We have previously established these index laws for positive integer exponents, in other words where our powers, where our indices, are positive integers. How could we extend these ideas to the situation where those exponents are not necessarily whole numbers? We want to now consider the situation where our exponents might be rational numbers. What do we mean by rational numbers? Rational numbers are fractions, a whole number divided by another whole number. And the set of rational numbers is denoted by Q. So if we have m and n in Q, in other words our powers are rational numbers, we are just going to carry over those laws for positive exponents. In other words, we will have that x to the m times x to the n is x to the m plus n, that x to the m divided by x to the n is x to the m divided by n, that x to the m to the n is x to the m times n, and that xy to the n is x to the n y to the n. Now it's important to realise that we are really in charge of deciding what these things mean. For example, our definition of powers so far don't allow us to attach any meaning to something like x to the power of a half, or x to the power of -3, or even x to the power of 0. If we meant by x squared take two lots of x and multiply them together, then we can't extend that definition to what it means to have x to the half. We can't take half of an x and multiply it together. We can't take -3x's and multiply them together. We can't take no x's and multiply them together and expect to get sensible answers. We are going to define what we mean by all of these kinds of terms by taking our usual index laws and extending them to rational numbers. So based on that idea, we do now have to try and answer questions like, what do we mean by x to the power of a half? Well, if we take x to the power of a half and multiply it by x to the power of a half, then we have an index law that says that this is x to the half plus a half. And a half plus a half is 1, so we have x to the 1. We don't usually bother writing that 1. So x to the half multiplied by x to the half gives us x. In other words, x to the half is a quantity that when you multiply it by itself, you get x. Well, that is what we mean by the square root of x. If you multiply the square root of x by the square root of x, you get x by definition. So, the inevitable consequence of our carrying over of these index laws to rational numbers is that when we talk about x to the half, that is the same thing as the square root of x. So, for example, 4 to the power of a half just means the square root of 4, that is 2. An extension of this idea is, what do we mean by x to the 1 over m, where m is a whole number? Let's investigate this by an example. Suppose we have an m of 4. So we would have x to the 1 over 4. What would happen if we multiplied that by another x to the 1 over 4, and another x to the 1 over 4, and another x to the 1 over 4? We would have x to the quarter plus a quarter plus a quarter plus a quarter. Well, 4 quarters is 1, so again we have x to the 1, or just x. In other words, this thing x to the quarter is the quantity which, if we multiply it by itself 4 times, gives us x. Well, that's what we mean by the 4th root of x. So again, it is an inevitable consequence of our definitions that x to the power of 1/4 is the 4th root of x. And therefore you can see that it is also going to inevitably follow that x to the power of 1 over m, where m is a whole number, will mean what is the mth root of x. So, for example, what is the value of 512 to the power of 1/3. That means the same thing as what is the cube root of 512, which is 8. What do we mean by x to the n over m? In other words, x to some particular fraction where we may have pieces on the top and the bottom. Let's look at this with an example. What could we mean by 2 to the power of 3/4? Well, using one of our index laws backwards, we could write that as 2 to the power of 3 to the power of 1/4, because we have a law that says a power to a power is the same thing as those two powers multiplied together. 2 cubed is 8, and the power of 1/4 means the 4th root, and that is probably about the best way that we can leave that looking for now. It's worth noting that there's more than one way of doing this. It would also be correct to say that we have 2 to the power of 1/4 to the power of 3, because if we multiply the quarter and the 3, we again get back to 3/4. So we could say that this is the 4th root of 2 all cubed. Both of those things would be correct. In general then, what do we mean by x to the n over m? It could either be x to the 1 over m to the n, or it could be x to the n to the 1 over m, and it may be better to write these as either the mth root of x to the power n, or x to the power n, and then we take the mth root. We now need to consider some negative indices. What do we mean by x to the -1? Well, if I have x to the -1, then there are many ways I could rewrite this using our index laws. One example would be x to the 1 divided by x squared, because 1 subtract 2 gives me that -1. So I could write this as x divided by x times x, and then I could use some cancellation laws to cancel that x with this x, leaving me just with 1 over x. There is our meaning of what x to the -1 means. X to the -1 means 1 divided by x. So for example, 3 to the -1 is just another way of writing 1/3. Taking that a little further, what do we mean by x to the -m? We could write x to the -m as x to the -1 times -m, which using one of our rules becomes x to the -1 to the power of m. We've just established that x to the -1 means 1 over x, and 1 over x to the m will be 1 over x to the m. So here is our general rule. When we say x to the -m, what we mean is 1 over x to the m. So for example, 3 to the -2 is the same as 1 over 3 squared. That is 1/9. What do we mean by x to the 0? We can't just say take an x and don't multiply it by itself at all, but we can use our new extended laws to come up with an idea for what this would mean. Well, x to the 0, we could write that as x divided by x, because this is x to the power 1 divided by x to the power 1, and 1 subtract 1 is 0. But we have the same thing on the top and bottom of this fraction, so therefore that is going to be 1. We have a conclusion. Anything to the power of 0 is 1. Well, I say anything, but we have to be a little careful here. We are dividing by an x to make this explanation work, and it's not possible to divide by 0, so we have to be careful here that x itself is not 0. It's a very interesting topic to discuss what 0 to the 0 comes to, and I shall put a link in the description of the video to something else you could watch if you're interested in that question. So if you were asked what 4,793 to the power of 0 comes to, you can straight away say that is going to be 1. We've looked at a variety of important cases, and here is a summary of everything we've just looked at. Let's use our new index laws to do some more examples. So, in A, what is x to the half multiplied by x to the 2/3? Well, we can just apply our usual rule that says we add the half and the 2/3. Easiest way to add fractions is to put them over a common denominator. A half is the same thing as 3/6. 2/3 is the same thing as 4/6. So therefore we have x to the 5/6. There's nothing wrong with leaving our final answer like that, but if it helps to make it clearer what we have here, we could write that we have x to the power of 5, and we've taken the 6th root of that. In part B, we have to have 4x to the halves divided by 3x to the thirds. Again, it is important to realize that this power of a half is only attached to the x, not to the 4. So we could write this as 4 lots of x to the half divided by 3 lots of x to the third, and then it would be good to split those fractions up. 4/3 times x to the half divided by x to the third. So we have 4/3 of x to the power of 1/2 subtract 1/3. Again, it's easier to deal with those fractions if we put them over a common denominator. 4 lots of 3/6 subtract 2/6. We have 4 lots of x to the power of 1/6, which is a perfectly good way to leave the final answer, but if you like, we could write that as 4 lots of the 6th root of x. Question C is expressed in decimals rather than fractions. You've got two choices here. You can either rewrite those decimals as fractions, or just leave them as they are. What is x to the 0.4 to the power of 1.5? Well, our index law tells us that will be x to the 0.4 multiplied by 1.5, which is x to the 0.6. It's quite nice to be able to notice some common decimals as fractions. This is the same thing as x to the 3/5. So if we wanted to, we could write this as x cubed and then take the 5th root. In D, we have to find the square root of 64 x to the 5s. Now, square root is a power of a half, so we have to find the power of a half of 64x to the 5s. And in this case, that power of a half does apply to the 64 just as much as it applies to the x to the 5, because the whole thing was under the square root sign. So we can use another index law to say we want 64 to the power of a half, and we want x to the 5 to the power of a half. Power of a half of 64, in other words the square root of 64, is 8. X to the 5 to the power of a half, all we can do is use our index laws to write that as x to the 5/2. Although of course we could choose to write that as a square root of x to the 5 if we preferred. We can also use these ideas just to evaluate numerical expressions. What is the value of 25 to the power of a half? This really is a question that makes sure that we understand that we know what power of a half means. It means square root. So 25 to the half, the square root of 25, is 5. Similarly, what is 81 to the power of 1/4? That means what is the 4th root of 81? That's 3. What is 16 to the power of negative 0.5? I think I would prefer to write that as 16 to the negative 1/2. Well, let's deal with the negative first. We know that a negative is the same as this appearing on the bottom of a fraction. In other words, we have 1 over 16 to the half. And 16 to the half means square root of 16, which is 4. So our final answer of 16 to the negative 0.5 is 1/4. And what is 321 to the 0? Nothing clever required here. Anything to the power of 0, except possibly 0 to the power of 0, is going to be 1.